Hi everyone, welcome. In this very brief video, I'm just going to go over two examples of creating canonical covers based on relation and functional dependencies. Not to go too deep into the actual background of the algorithm, but I just wanted to rewrite it here based on what you're expected to do as an algorithm. And you may have other ways to do it, which is fine, but this could be a useful way if you're a bit confused on how it works. So essentially, the rules that are provided to you are on this slide here. This is the algorithm provided. Essentially asks you to make a canonical cover or a minimal set by removing any extraneous attributes. And the whole purpose of this exercise is to do just that, remove any attributes in our functional dependency list that are not needed, and to get the minimum amount such that all of our functional dependencies originally provided imply this minimal set of functional dependencies, and vice versa, all the minimal sets of our functional dependencies imply all of the functional dependencies a part of some relation. Okay, so rewritten as this, the step that I would recommend is you first look at your functional dependencies. Let's take a look at this F down here, and you apply the unity rule to everything that's on the right-hand side of your functional dependencies. So whatever's on the right of the arrow. So here we essentially say we apply the unity rules to break them into individual ones. So B and C kind of sticks out to me here. We might need to apply the union rule. After we do that, we go ahead and we take a look at our left-hand sides of our functional dependencies, and we try to see if there's any extraneous attributes that need to be removed so that we can have our minimal set. Okay. So these rules here are just rewritten from the previous slide, but for our purposes here, I just want to go through a step-by-step process of this. Again, this is going to be a bit redundant at some points, and it might get a little convoluted if I keep repeating some letters. But essentially, I just want to show you a process that you can write down and translating it to paper and pen or in your Word document as well. Okay. So based on the problems you're given in your quiz and homework, you're going to be given a relation and then a set of functional dependencies F. And for our purposes here, we have A implies BC, B implies C, and AB implies D. So our first step here again is to apply our union rule. So let's take a look at our functional dependencies. Is there anything that's double on the right-hand side? We see we have BC right here. So let's go ahead and take a look at what this could become. Sorry about that. So we can see here that A implies BC can be broken into A implying B and A implying C. And what I want to reiterate here is that when you're doing your canonical cover, you no longer look at this F. Whenever you make a modification while you're doing this, you always take your most recent one. So you can kind of think of this guy as being deleted up here. Don't look at this top one. Now F plus is the one we're looking at. So now we don't have any more extraneous attributes or double attributes on the right-hand side. We have B, C, C, and D. With the new F plus now, we can try to look at the left-hand side, okay? So if we take a look at the left-hand sides, we have AB is implying D. And what we're trying to look at now, this is a bit more complicated, is we're going to say, can we imply A into D or B into D? AKA, do we need both A and B, or are one of these a bit extra for us to look at? Okay, so this is one approach you could take. I'll show a different approach later as well, so you can pick and choose whichever ones you like. But again, whenever you're asked to do this as an algorithm or anything like that, you just write down your steps, very similar to what I'm doing here. And as you get into it, you can remove the amount of information you need to say, but just show each of your steps when you're changing them. Okay, so again, when you're looking at this AB over to D or something similar, we're trying to ask if there's any extraneous attributes. So you can actually ask in English, you could say, can I calculate this functional dependency without needing one or the other? So essentially, if I have a functional dependency CD, which implies E, and I can calculate D using only C, I no longer need D inside this original functional dependency, as I can calculate D elsewhere, okay? So essentially, if we're trying to ask, can I remove either one of these because I can calculate them somewhere else at some point? Or essentially, one of the other guys can calculate them. So again, to reiterate, we're just trying to see if we can minimize our functional dependencies so that they're not so extraneous with their attributes, okay? Because again, we're trying to get to that candidate keys, and we're trying to make sure that we have our minimal set, okay? So to actually go through this process, you first think of your relation, AB implies D, and we say, okay, is A extraneous? So can we calculate A using the closure of B? And again, to rewrite this, if I can get A using the closure of B, I don't need A anymore in my functional dependency, because I can get that guy somewhere else. So if we take a look at our closures, again, this is something that we looked at earlier. Our first closure is always going to be B by itself, so it's reflexivity. So B is going to imply B. And then from this one, we can also see, if we take a look at our original F plus up here, we get C from here. So B is also implying C. Now, if we take one more look here, let's see what else we can get. We are looking at B implies C. It looks like we can't get anything else here. We can't really mess around and try to get anything else from implying B. Also, try to remember that we're not going to be looking at A, B over D right now in this closure. We're trying to see if we can get to A. Okay? So, because I cannot get and calculate A using B's closure, I can only get B and C, we can assume for right now that A is not extraneous. Now we ask the other guy, is B extraneous? Can we calculate B using the closure of A? Let's take a look here. We see that A implies itself. We also see that we have A implies B over here, applied from A over to B, and we also see that A implies C. So we actually can get a bit more information from this closure. We can get A, B, and C, but the most important thing here is that A implies B. So because of this, we can determine the other attributes and B itself without B, therefore B is extraneous. It doesn't matter if, like, for instance, if A to C wasn't here, that wouldn't make a difference per se, because we could still get to B. So again, to reiterate, what you're doing here when you're using the left-hand side part of your algorithm, when you're trying to check for extraneous attributes, what you're saying is, can I imply the other attribute in this set of two attributes using this current one? And if I can, then I don't need this guy on my functional dependency anymore. Okay? So now, because we removed this extraneous attribute, we recreate our original F, and now we have A implies B, A implies C, B implies C, A implies D. Okay? Now we go to our third step, which is where we try to find any redundancy or try to repeat our algorithm from before. And again, we're looking at the right-hand side, left-hand sides. It looks like everything is pretty similar for us right now. So the next part that we need to look at is we're going to look at all of our functional dependencies, check if any of them in our functional dependency list can compute the closure of the attributes if we remove it. So what we're trying to do here is kind of cull our functional dependency list down until it's a minimal set. So in easier words, we're trying to see if we can remove any of our current of these functional dependencies and still be able to calculate everything else in our set. Okay, so this is where it gets a little bit more redundant of a process, but I'm going to go through this step by step here. So the first step you can do is say, all right, I'm going to shut out A over to B, and I'm creating this new functional dependency list. A implies C, B implies C, and A implies D. So after I calculated this guy, I'm just going to calculate the set of A here. And what we can see here is that our closure of A can calculate itself. Our closure of A can calculate C, A over to C. Our closure of A can also calculate D. So this is looking pretty good, but for instance, we are actually missing B still. Okay, so how else using these functional dependencies can I calculate B? Well, I can't. So what that tells us is that this A over to B is not redundant and that we're going to need it in our code. Okay. We have another functional dependency now of A over to C, so we're going to remove that. Now we're left with A implies B, B implies C, A implies D. Now, if we go ahead and recreate our closure of A, and one more thing is that you don't need to pick A each time. Essentially, rule of thumb is that if I'm removing A over to C, you can now try to calculate the closure of A. Essentially, can you calculate whatever you removed closure, the left-hand side of what you removed, that one's closure. So A implies itself. A also implies A and B, because A over to B here in our functional dependency. A is also going to imply D based on this relationship right here. And now we're also able to figure out our C here. And where C came from is using our axioms from earlier, is that if we have A implying B and B implies C, then we can also know that A implies C as well. Okay? So if we removed our A over to C functional dependency, and we're still able to calculate every single attribute of this closure, we know that it's redundant. Essentially, this functional dependency we originally had wasn't really doing much for us. So now what we know is that because it's redundant, we can create a new canonical cover where I have A over to B, B over to C, and A over to D. Okay? You repeat this repeatedly until the end here. So B is over to C, remove that guy. You have 2 more left. I'm going to go through these a little bit quickly, but essentially calculate your reflexive closure, see what else you can get. A implying B, A also implies D, but you'll see here that we can't get C, so our B over to C is not redundant. Again, remove A over to D, we get A over to B, B over to C. Likewise, we can get A, B, and C pretty easily, but we cannot have access to D whatsoever. So in our closure, it's not redundant. Okay? Cool. And at the very end of this, after this work, we have our canonical cover. So now, because we know we went through every single functional dependency that we've reduced our set to, and we checked for redundancy, we now know that it is not a redundant functional dependency, and this is the minimal set that satisfies those 4 things that we were looking for earlier. Okay, cool. So this is the first part. I'm going to go through another example that's a little bit more complex here, and it shows a little bit of a different way. But if this is making sense, you can apply this to your homeworks. And this algorithm per se, just show your work and show your steps. You don't need to follow this per by the book, but essentially try to go through this process. The main thing that I want you all to use here is essentially look at the right-hand side of each attribute. That should be your step 1. Check the left-hand side after that, step 2, and then go ahead and reduce from there. And after you do that, you should be able to calculate your canonical covers. Thank you.